So slides for every week I post in the Slack channel, which you are hopefully a part of. Not the club's general Slack channel, but the one for intermediate specifically. Okay, we'll go ahead and hop into it then. So last week, we went over a little bit about visualizations, some basic exploratory analysis using Altair a little bit. We took a look at the notebook. We did some work with basic Altair functions in the Titanic data set. We're going to go ahead and continue with that for a little bit for the first half of today. But we're going to be using a little bit of Matplot and Seaborn, which are sort of related to each other, just to see what the differences between those two are. So you're all probably familiar with importing data sets into your terminal, into your editor, but for those of you who will be using files that are not necessarily on your system locally, this is another way to do it, so that you can have your data and pull it down from some sort of repository, which is where you'll likely be storing it. This is just a way to do it through GitHub specifically. This comes from one of my own repositories, and you can do this with pretty much any public repository as long as you have the link. As you'll see here, all of the CSV files are available online. So instead of pulling it down, downloading all that stuff, you can do it that way. And as you can see here, the data frame with all of our relevant information is present. So we want to make a few different kinds of visualizations using this Titanic data set specifically. And there are a few different ways to do that. We'll go over a few different kinds, namely histograms, box plots, scatter plots, and then a little bit of bar chart stuff at the end. But for histograms specifically, these are all pretty straightforward, and I'm sure some of you have done this before, but if you were looking to create a histogram for some sort of variable, we'll say we'll use age, because age in this case is going to have probably the most consistent distribution. We would plot it, and of course with every histogram we're going to want to specify, as opposed to using frequency, we're going to use density as our y-axis value. We'll go ahead and put a few labels on this. Just so we can have this be more easily read by anyone else who's looking at it. And as you can see, this gives us a pretty good histogram of passenger distribution by age. And from this, it's pretty easy to tell that the majority of our passengers are between the ages of 20 and like 30, 35. So that's a good way of getting a sense for what the distribution of a certain value in your data set is. If we were to set this to false, you'll notice that we're no longer measuring on a scale in terms of probability. Our values are now just counts. Okay, this is like a frequency histogram. So this is essentially what a bar graph is, but we'll keep that as true for the time being. Box plots we also visited with Altair, and this is a good way to get a sense of some of the base statistics of some of our variables. If we have outliers, it's also a very good way of distinguishing that. In this case, we use fare, which is essentially like the ticket price that each passenger paid to get onto the Titanic, and At least for class 1, we see that there are a lot of outliers sort of in the upper range. So some people must have paid a very high price for their ticket. To do this in Seaborn, relatively simple. And we always abbreviate our package name. That's just the way it's been imported into this notebook. And that's generally, these abbreviations are just usually what is used. It's not necessarily something I made up. That's just usually how it's abbreviated for the sake of simplicity. So in this case, we wanted to compare fare by class. And we'll set the title to something simple. We get something that looks like this, right? It's more or less a replication of what we've done in Altair above, and it shows all the same things. If we wanted to redo that, but without the outliers that we have present, we could very easily replicate it with this argument that is show and this effectively removes any outliers that we have. Scatter plots are, as we said last week, a good way of comparing multiple continuous variables in our set. So say we wanted to compare, we'll choose, I guess in this case, we'll choose age this time. And we'll compare age to the fare that each passenger paid. We'll use the data frame that we defined above, and we'll give it a different color instead this time. And then we end up with a nice visualization. You can change the types of the points, so you can change the shape, you can change the color, you can do all of that. The documentation is pretty easy to parse through if you actually want to customize your graphs a little more. And last but not least, the bar plots, which we're going to use to analyze the differences in the types of people that survived, using the label, which is survival versus not surviving, 0 or 1. And in Seaborn, this would be denoted as count plot because we're essentially taking the counts of the members in each class. So we'll do this by class. Our data set is the data frame that we had before. And since we have multiple categories for our one label survived, which is we have a label for 0 and a label for 1, that's 2 different groups. We're going to separate our hue, which is essentially the color that it's going to turn out to be by the variable survived, which is the result we want to show. And we end up with something that's very similar to what we did above here, except in this case, instead of showing their survival rates on top of one another for the counts, it shows them as bars next to each other. Right, and of course you can change this out if you wanted to look at survival by gender. We would do this as well, and it would still work. You can mess around with these kinds of visualizations and give you good insights into the kinds of trends you have in the data. In this case, you'll notice that the proportion of women that survived the Titanic is significantly higher than the proportion of men that survived. So we'll jump right back into the actual lecture for today. Again, all this is posted in the Slack channel, so if you have trouble accessing anything, all the links are in the Slack. the Zoom link for this session. All right, I'll go ahead and give that to you. Let me know if that works for you. And just so you all know, the recordings are always posted every week. The recording for last week should be in the Slack channel already. Okay, we'll go ahead and hop into this. I'll actually reshare that. This week, we're going to talk a little bit about data cleaning, and that's essentially the next step in our process. Data cleaning is the process of, people also like to call it data engineering. It's another way to say it. It's essentially the same thing. We're taking whatever data that we do have, maybe it's like a big table or like a CSV file or something, and we're doing some sort of pre-processing for it. So that's ready to be put through an algorithm that we have built or will build as soon as our pre-processing step is complete. From the past lessons, we came away with this idea that machine learning is essentially just finding relationships between different features, right? So these things are essentially just a way for us to make inferences about information that we do currently have for use in the future with data that's new, data that we haven't seen before. And in order to make these inferences about the future, we have to use data that currently exists, observations that have already been made. So I like to think about this scenario as a good example of what is not a good practice in data science, and that is, imagine you have this scenario where you're trying to build some sort of algorithm that's a classifier, which is supposed to identify whether or not an image that is fed into the system has a car in it or not, right? So pretty straightforward. Is there a car? Is there not a car? That's what we call binary classification. Imagine if we had a data set of a ton of images, some with cars in them, some without, and the data set looks something like this. Right, of the images that we have here, some have cars in them, some do not. But there is one critical problem here, and I'm sure you all know what that is. Every single car image that we have in our data set is a very vibrant shade of blue. So when we actually use this training set, as we will call it, to create our classification algorithm, we might very well end up with an algorithm that does a great job of identifying not necessarily what we intended it to do, which is pick out cars and photos, but rather does a really good job at picking out blue objects in photos. Something that is ultimately an unintended consequence of us using only a very select few images in what we would call a biased data set. And this isn't just an abstract problem that data scientists have to worry about. We actually have encountered this problem before. Very famously, there was this one facial recognition algorithm that scientists developed that when fed a picture of a very like de-resed Barack Obama, sort of recreated the face into a man that looks very much not like him. And the problem with that was that they found that their data set was biased towards people of Caucasian origin, and they hadn't even realized it, which is why they got the result that they did. So having a biased data set can sometimes have very severe consequences in terms of sabotaging the accuracy of the result. And that's why we have to look out for it. So the way to deal with data cleaning in the beginning of your project phase is to make sure that your data set is basically scrubbed of any missing values or any issues or discrepancies with the actual information that it stores, right? If you look at our our snippet we have here of our Titanic data set, which we just visited, you'll notice that there are a lot of values here that are missing. So all these NaN values, essentially Python's way of showing a missing value, are present in terms of this cabin feature here. Some people's ages are not present, so that's another thing we might have to address. So just having a quick glance over this, we already know that there are some issues that we need to deal with before we even do any sort of analysis or statistical inferencing on this particular set. Why do we deal with missing values? Well, a lot of the time our algorithms won't even process data that is missing any sort of information to it, right? If it encounters anything that's not present, it might not even work at all, which is obviously an issue down the line that we want to avoid. Dealing with missing values for our intents and purposes is relatively simple. You mostly, for the most part, have two different options, one of which is deleting information entirely. Usually that's deleting individual entries, which are rows, or certain features, which are columns, that happen to have a lot of missing values and aren't necessarily ready to be used. We can also impute values for those that are missing, which is essentially adding in a value ourselves for those that are non-existent, right? And we have a few different ways of doing that we can talk about. It's a little more complex than just deleting rows that have missing values in them, but it doesn't necessarily need to be that complicated. There are very complicated ways of doing it. There are also very simple ways of doing it. And we'll give some examples of those. So you've probably heard of this before, but imputing by mean, or in some cases median or mode, in the case of categorical variables, is one way of dealing with it. And the upside to this is that it's very simple to just take the mean. Say we have this data set that's sort of like a mock set here. We could feasibly take the average hours of sleep that people have per night in this example, which I suppose would be like a survey or something. Take the mean of sleep and put that value in for all values that are missing. So say we do this calculation, the mean sleep across all participants in this survey is 7 hours. We'll put 7 hours for everyone that didn't have an entry for sleep. And we effectively deal with our missing values that way. The thing we do have to watch out for in this case is that doing any sort of imputation can unknowingly introduce some amount of bias into our data set. And that's something we always want to keep in the back of our minds when imputing anything that's missing, or making any other modifications to our data set for that matter. KNN imputation is also something that will come up in the future. It's just another way for imputing values based off of an estimate. In terms of mean imputation, a mean is really just an estimate for what approximately the value of any variable might be. In this case, it's more or less the same thing, except instead of taking the mean of the entire data set, we're essentially taking an estimate based on the nearest neighbors of that one particular variable. And there's more information on that. You can take a look at these slides later and read up a little bit on it. It's a very interesting statistical topic if you're interested in the theory behind it. We will talk about KNN as a data science method a few lessons down the line. As opposed to imputing data, we can also delete data entirely. And this is something that ultimately you, as the data scientist, will have to make the judgment call on. But there are some general rules that you can sort of use as a guideline for making your decisions about this. One of which is you can delete columns, which are features like age or fare for our Titanic data set, or rows, which are observations, individual passengers, when there are large amounts of missing data for either. So say there's one entry, one person just didn't have an age or ticket price or class or anything recorded for them. In that case, it might just be easier to take out individuals that don't have much information associated with them. Same goes for features. So say, for example, the ticket price, the fare feature column had like only 30% of the passengers had a recorded value for that particular feature. It might just be easier to not use the ticket price at all and just use other features in the data set that are a little more complete. The other case is in which you can delete rows as you can afford to in order to not shrink your data set too much. And that is something you might do in the case where data or information is missing randomly. And we'll talk about what missing at random means. There's a little bit of theory behind it, but it's just something to keep in mind. So looking at our little like sleep survey sample data set here, it's kind of difficult to tell if these individual entries here are missing at random or not at random. And there are actually different kinds of randomness in terms of statistical theory. 3 different types to be precise, one of which is missing completely at random. There's also missing at random, which is kind of a misnomer, and I'll talk about why that is. And then there's not missing at random, which is the case that we need to be most concerned about, because there's usually a reason why data is missing that is relevant to our studies in that case. Missing completely random is just about as accurate as it sounds. So in the experimental case, say you were doing a data science project on the COVID test that students at UCSB take, and you notice that some of the entries for some students are missing. Missing completely at random would be in the case that maybe the lab just misplaced some samples or had inconclusive results, not really related to the students at all. It's just there was a little bit of bad luck, and some samples were lost that way. That would be missing completely at random. Missing at random is a little more common. Another way you would define this is missing conditionally at random, and that means that the missing data entries are missing as a result of some variable in our data set, but not necessarily the variable that we're looking to have a result on, which in this case is the stress level of individuals based on different features about themselves. So in this case, say we notice that all of our missing values are here because male participants in this study, for some reason, were less likely to record how many hours of sleep they got per night, and notice that each of the missing values here are marked male. So maybe that's a reason why. There's obviously a correlation between one aspect of the participant and their missing values. So the sex and sleep per night are related in some way, but it's something that we are aware of and has a clear reason for, and is not necessarily associated with our response variable, which is stress level. So another way to think about this is our missing values are conditioned upon some other feature in our data. Not missing at random is sort of the opposite in that you'll notice that our missing values perhaps are present as a result of the variable at hand, which is stress level. So for example, maybe those individuals who participated in this study did not record their hours of sleep per night because they were very stressed, right? So people with low stress levels did not report how much sleep they got per night. And since that is, a direct relationship between what our response and our missing values are, this is something that is not missing at random. There is a reason why people are not reporting sleep, and it does very much have to do with the result, right? So that's sort of a confusing concept that I wouldn't worry too much about, but it is something to keep in mind when you're doing your projects. Don't worry so much about classifying whether or not stuff is missing at random or completely at random or whatever, but do ask yourself a couple of questions when you're looking at your data set, and that is, one, why might this piece of data be missing? Could there be a reason for it? And two, what about this row or column is important to what I'm trying to do, right? If you determine a specific feature or anything like that to be important to your project, you're going to have to take a little more consideration as to how you deal with missing values in that particular feature. So in this case, if we were trying to predict stress levels of individuals based off of their hours of sleep, we can certainly drop individuals that didn't report sleep. We can also take the means of certain values too and impute them back in. Something to keep in mind, the train test concept we talked briefly about before. We'll talk a little bit more about it later on. But if in the case of separating your training and test set from your entire data set, you want to always treat your test set the same way you treat your training set, in the way you clean it, in the way you evaluate it, just because they should all ultimately come from the same distribution. Obviously, we would want to treat these two sets the same way, without necessarily carrying over information from the training set and the test set. We'll talk about bias in that respect a little later on, but keep that in mind for now. Yeah, and that's all I have for you guys this week in terms of data cleaning. We'll go over a little bit more. We'll have a little like hands-on activity with data cleaning in the Titanic data set next week. But if you want a head start on that, please do take a look at the week 3 notebook that has a lot of good information about imputation in there. And also remember that this Friday there is a trivia night social. The link is on the calendar, the data science calendar. It is at 5 p.m. Make sure you head out to that. And good luck with midterms, everybody. I know it is midterm season once again. But regardless, thanks for coming out. Links for all of the information for today are posted in the Slack channel, as I've said before. It's also at the end of each week's slide deck, so I have all the information here for you that you can look at.
Thanks, Harper. This was great as always. Have a good week.
You as well. Thank you for coming out.